wait a second. Okay, started recording and start this thing. Okay. All right. So we continue from where we left off in the 10 a.m. to 11 a.m. live session. I have a few more things to discuss. These are straightforward things. As I was saying earlier, we do have to do a little bit of algebra, but since you have not been exposed to these things previously, it's good that I show you the important steps without going too much into the algebra. So the next thing that we're going to obtain, or we are going to go to, after obtaining these expressions for the sigma rr and the sigma theta theta in terms of the epsilon rr and epsilon theta theta, is just to substitute for this epsilon rr and the epsilon theta theta the expressions from the strain displacement relations. Okay, so now we use the strain displacement relations. Now we use the strain displacement relations, remembering that we get to use all the simplifications which plane strain and the axisymmetric conditions allow us. So we use the strain displacement relations in the simplified form. Simplified means simplified following from plane strain conditions and axisymmetry. So what we are going to basically end up with is that epsilon rr is simply du dr. Please note that this is not a partial derivative anymore because u is now only a function of r. Had u been a function of both r and theta, then this kind of del u del r would have been necessary. But since u is a function of only one independent variable, we have only this kind of an ordinary derivative. So epsilon rr is equal to du dr. And epsilon theta theta, that is going to be equal to u by r. And if I just change my screen back to the tutorial sheet number 5, you can actually see this from here. That epsilon rr was just this partial derivative of u with respect to r that has changed into an ordinary derivative. And epsilon theta theta, it had this 1 by r del v del theta term. So either you can think of this term not being present in terms of the fact that v is equal to 0, or in terms of the fact that the del theta of anything is equal to 0 because of axisymmetric condition. So the only term that survives in that epsilon theta theta is this u by r. That is why I have written in this here, this epsilon theta theta is equal to u by r. So all that you have to do is substitute this one and this one back here. And when we do that, we obtain for our sigma rr this thing. And for sigma theta theta, we obtain this. So now you can almost guess what I'm going to do next. Remember that I had this equation del sigma rr del r plus sigma rr minus sigma theta theta by r is equal to 0. This is what equation? This is the stress equilibrium equation in the r direction, this equation. Okay, so I'm just repeating it here. Please note that this is r. So this is that same equation. All that I'm going to do is substitute these two equations in this equation. If I do that and do all the simplifications involved, then the equation that I'm going to end up with is this thing. So it takes about 3 lines of simplification, little bit of algebra involved, plus minus. Ultimately, you will end up with d square u dr square plus 1 by r du dr minus u by r square is equal to 0. This is a very important equation because right now we have obtained this equation in the context of thick walled pressure vessels from this equation, from this governing differential equation. This is the governing differential equation. Here we have substituted basically the strain displacement relations together with the stress strain relations, and we have obtained this. But this particular form of equation in the displacement variable u, first of all, you note that this is an ordinary differential equation. The order of this equation is 2 because the highest order derivative appearing in this equation is 2, is d square dr square. The next one is ddr. So the highest order derivative is second order derivative. So it's a second order equation. But this is a linear equation. Okay, this is a linear equation because in none of the terms you have anything like u square or u cube. Furthermore, you also do not have terms like this du dr times du dr. Okay, this kind of term is not present, nor do you have the presence of u times du dr. This is also not present. Had this one or this one been present in this equation, then that equation would have been a nonlinear equation. Those kinds of nonlinear equations are very hard to solve. Compared to that, this kind of a linear equation is relatively easier to solve. Now, I don't know whether you know of the various tricks which are required to solve these equations, because if you just throw this at symbolic Python, it will give you the answer in 2 seconds. Okay, but as part of your general training, it is good to know about some mathematical tricks which are used to solve these kinds of equations. Plus, you also try to understand that this kind of equations will also be important later on when you study things like heat transfer. Even though this particular form may not appear directly, but something like this will appear. This may also appear in your studies of fluid mechanics while you are doing exact solutions. Not this exact form, but things like this. Now, what do I mean by things like this? Well, you see, there is a very nice thing going on here. And if you identify that thing, you can actually solve this equation rather easily. You see, here there is a second order derivative. Here there is a first order derivative, but there is additionally a 1 by r present. And here there is no derivative, but there is a second order reduction through this divided by r square present. So it is our guesswork, a very educated guesswork, that we can say that the general form of the solution will be like this: u is equal to r to the power m. Now, this is certainly a guesswork. It is nothing more than that. That we are guessing that our solution will be of this form. But why this kind of a drastic step? Well, the theory of linear differential equations tells us, or the theory of differential equations tells us, that if we have a linear equation, it is going to have a unique solution. Now, this unique solution is a very good news to us. It is a good news to us because if you can somehow, by some hook or crook, you can even guess a solution to a linear equation, you are guaranteed that your guesswork, if it is actually solving the equation, it is a correct guesswork, because that is the unique solution that you will have to your differential equation. So the idea is like this: if something has a unique solution, and if you're somehow managing to obtain one solution to it, then you are guaranteed that that one solution is the solution to that differential equation. So based on that kind of a general idea, we are going to guess that u is equal to r to the power m is actually going to solve this. And we're just going to find the condition under which it is going to solve it. So this is not too different from the kind of general solution methodology which you used in your first year mathematics to solve differential equations, where you probably solve differential equations by saying that you are going to take the form e to the power mx. So just like that was a guesswork, this also is a guesswork. Okay. So what happens if we substitute u is equal to r to the power m here? Well, what you obtain is this. M times m minus 1 r to the power m minus 2 plus m times r to the power m minus 2, because here there is only one derivative, so one that m comes from there. But this m minus 2 is happening because first of all it is becoming m minus 1 because of this ddr, and then there is another 1 by r because of which that is becoming r to the power m minus 2. And finally this is just r to the power m minus 2. So overall from here what we are going to obtain is this. You see, the best thing, okay, about this thing is that here you have r to the power m minus 2, here you have r to the power m minus 2, here you have r to the power m minus 2. This is the key observation which motivated us to take this r to the power m form, okay, because that r to the power m minus 2 is going to get cancelled from all of these three terms. So let me go to the next page. So this is going to give us m times m minus 1 plus m minus 1 equal to 0, and that is simply m square minus 1 equal to 0, which is simply m is equal to plus or minus 1. So the two conditions which you obtain for r to the power m to be a solution of your governing differential equation is that m is equal to plus 1 or m is equal to minus 1. And based on this, we can construct our general solution for u by writing it as a1 r to the power 1 plus a2 r to the power minus 1. So this is simply u is equal to a1 r plus a2 by r. Please note that this a1 and this a2 are yet are still unknown constants. Okay, these are unknown constants. We have to find them out. How do we go about finding them out? Well, if you have been paying attention in your first year mathematics, then you know that for a second order differential equation, which is what you have here, basically, there is a second order equation. Second order linear differential equation. Okay, basically what you have here is an OD, ordinary differential equation. For such an equation, for a second order differential equation, in order to solve this completely, you need two boundary conditions or two conditions. Where do you get these two conditions? Okay, this is not just some arbitrary mathematical problem. So we have to connect this somehow to the physical condition. Now, ideally, what we would have wanted to have was that two conditions in terms of this displacement variable u directly, but we don't have that, because if you go back to the diagram of the pressure vessel, you have nothing directly in terms of the displacement here. Through our ideas of elasticity of various kinds of equations, we have obtained a governing differential equation in u, but nothing in this physical problem is directly in the form of the displacements. So what can you do? So if you think about it, the situation is like this. The actual loading conditions are in the form of the pressure. That pressure is basically like a sigma RR. It's a stress in the radial direction. So at the outer radius, you have some value for the sigma RR, and at the inner radius, you have another value for the sigma RR. And perhaps it is all right to provide our boundary conditions in those terms, and you will see that it is actually enough. Okay, so what we are going to do is this. For the boundary conditions required to solve for a1 and A2, we are going to use the condition that sigma RR, that is the stress in the radial direction, at the inner radius is equal to minus Pi. It is minus Pi because you understand that at the inner radius, so if this is our inner radius Ri, the pressure is acting in this direction, but the stress component, the radial stress component, that is like this, sigma Rr. Correspondingly, at the outer radius, this is our stress component, but the pressure is acting like this, inward. So at the inner radius, the pressure is acting outwards, the sigma Rr is acting inwards. That is why sigma Rr at R equal to Ri is equal to minus Pi. Similarly, you have sigma Rr at the outer radius, that is also equal to minus Po. Po means P outer, Pi means P inner. These are the two conditions. Now these two conditions have been written in terms of sigma Rr, but we have the solution in terms of U. We have the solution in terms of U. So what we have to do is to express the sigma Rr in terms of the U. And that can very easily be done. In fact, we have already done that. So sigma Rr we have already expressed in terms of epsilon Rr and epsilon theta theta. So we can take a look back. We have obtained this sigma Rr in terms of this epsilon Rr and epsilon theta theta. And subsequently, by using the strain displacement relations, we have obtained this sigma Rr in terms of the U. And we are going to use this thing. So all that you have to understand is that when you do this du dr, you have to evaluate this du dr at r equal to ri and this u by r at r equal to ri. Similarly, for the sigma theta theta, we have to obtain this u by r at r, not for the sigma theta. When we go to the outer radius, we have to appropriately substitute r equal to r naught and r equal to r naught. Okay, so let's get back to the thing and let me write down the expressions. So minus Pi, that is going to be equal to so after some simplification, you are going to obtain this A1 minus 1 minus 2 nu A2 by Ri square, and from the second boundary condition you are going to obtain minus P naught divided by P naught is equal to E by 1 minus 1 plus nu 1 minus 2 nu E1 plus 1 minus 2 nu A2 by R naught square. Okay, so RO square. This is the inner radius, this is the outer radius. Now you have, so please note that this Pi is known to us. This PO is known to us. Ri is known to us, Ro is known to us. So all that we don't know are this A1 and A2. So basically what you have is that this is one equation in A1 and A2, this is another equation in A1 and A2. Considering both of them together, these are two linear simultaneous equations in A1 and A2. So if you solve them together, you are going to obtain A1 and A2. I'm not going to write down the expressions for A1 and A2. Rather, I'm going to go ahead another step and give you directly the expressions for sigma Rr. So sigma Rr will be C1 minus C2 by R square, and sigma theta theta is going to be equal to C1 plus C2 by R square, where C1 is equal to Pi Ri square minus Po Ro square divided by Ro square minus Ri square, and C2 is equal to Pi minus Po times Ri square Ro square divided by Ro square minus Ri square. Now this seems like horrendous looking expressions, but there's a nice symmetry to it. Okay. Now, very importantly, what we can do and what I will of course ask you to do in the tutorial problems is that you can take special cases. For instance, one of the most important special cases is to say that what happens if you take PO equal to 0 and just consider the influence of Pi, because that is exactly like the kind of situation which you did in the case of the thin walled pressure vessel, where you considered only the gauge pressure. Okay, so you will see that it is very much possible to reduce the expression of this thick walled pressure vessel, the sigma RR and the sigma theta theta, to the expressions that you had studied in the context of the thin walled pressure vessel. Okay, where RO minus RI is equal to T. And I will of course ask you to do those things. You can obtain many other special scenarios from these simple, or not simple, I would say, from these algebraic expressions for sigma RR and sigma theta theta. And just one curiosity, you note here that sigma RR plus sigma theta theta is equal to twice C1, which is basically a constant. Okay, and since this is a constant, sigma ZZ, which was equal to nu times sigma RR plus sigma theta theta, that also is a constant. Okay, so this is a very, very important consideration, which is important for interpreting the results which you are going to derive. Okay, so in the tutorial problems, I will proceed in a very step-by-step fashion to help you obtain the different expressions which are important in different contexts, and you will get a fair idea of what is going on. And it is very easy to plot this out also, and you can get a very nice intuitive feel about what is going on. So with this, I will end this discussion on thick walled pressure vessels. And
excuse me, sir.
Yes.
Sir, in second question, is it not A1 minus of 1 minus 2 mu into A2 by R?
Which one?
Sir, in minus P naught equals to E by
this one?
Yes, sir.
Maybe I've made some algebra mistake there. So I'm referring to my copy. I have written this as plus. Let me just check. Okay, just give me a second. I'll have to check. Okay, so I'll check and let you know. Okay, so for now, let this be a doubtful case. Okay, so I'll check that. Okay, so with this, I'll end this class. Thank you very much and have a nice week. Bye.
Thank you.